All right. First of all, sorry I'm late. Well, it wasn't my fault, I promise. Yeah, so for those who haven't seen me yet, I started here as assistant professor at the UvA, USoft, December 1st. I gave a talk here in June, I think it was, but now it's a bit more less high stakes situation, I guess. Yeah, so I'm gonna tell you about some of the research I've done in the last 2 years-ish. We'll see how far I get. I have quite a lot of stuff I want to cover, but feel free to stop if you ask any questions. Yeah, because I want to start with an introduction to select calculus. If anything there is not clear, then feel free to ask. So yes, what I'm going to talk about is actually 3 results in 4 papers with a bunch of co-authors. So most of the talk will be about the first result, which is joint work with Alex Kissinger and Renaud Villemar. And then the second 2 results are from some recent preprints with Julian Kotze and Thomas Lakonen, who are 2 master students I supervised. That work is mostly theirs. I was just there in the supervisory capacity, but yeah. Okay, so let's get started with an introduction to select calculus. So first, select diagrams. So you can think of these as just as a start, just as an alternative notation to quantum circuits. Okay, so if you have a quantum circuit, you can sort of translate it one-to-one to select diagrams, where instead of having these names in boxes like S and X and T and H, we have these nice colored little dots. We have these green dots that I will call Z spiders. I will give a formal definition later. And these red dots, which are X spiders. And you see there's a phase in there, and this phase sort of tells you how much you rotate among the block spheres. So if you recall an S gate, it's like a pi/2 rotation on the block sphere, so we write a pi/2 in there. A T gate is pi/4 rotation, pi/4. And we see that the C0 gate becomes this connection of a green and red dot, and it will become clear why this thing is a C0 gate. And then once we have these gates, we can just take a quantum circuit and like just change it gate by gate into a select diagram, which represents the thing. And there is a good reason to do this, I promise. So first, a formal definition. So with these colored dots are spiders. So while a quantum circuit is built out of gates, a select diagram is built out of spiders. And these are a type of linear map. There's a family of linear maps, actually. So these spiders can have any number of inputs and outputs. And they represent a sort of projection operators. You can think of them as generalized Kronecker deltas, especially the Z spider. So it says that all the inputs should be 0, and then all the outputs will be 0, or all the inputs should be 1, and all the outputs should be 1. But then you get a phase e to the I alpha. And the X spider is the same thing within the X basis, with the Hadamard transform basis. As an example, if you have a single input, single output, this is just a unitary gate. So we can see, we can just calculate the matrix of these things, and we indeed get like the Z phase gate, and we get an X phase gate. Although in general, these things won't be unitary, it's just for one input, one output, they happen to be unitary. If alpha is 0, I won't draw the label. So it's just like a single colored dot. And yeah, so as I say, we can also have non-unitary things. So we can have, for instance, state preparations. So if I have an X spider with single outputs, well, this is like per definition, it's plus, plus, minus, and this is up to a factor square root of 2. It's the ket 0 state. Okay. These square roots of 2s will pop up here and there in select calculus. Often I will just ignore them because they're not really that interesting, but you need to carefully track them if you're actually doing calculations on like amplitude classical simulation. Okay, so these are just the spiders, and we build select diagrams by composing them. And we can compose them in 2 ways. We have vertical composition, which corresponds to tensor products. Same thing as in the quantum circuit, of course. So we can take tensor products. Here with the X spider, we could take a tensor product. This is just all sort of standard linear algebra things. And then the other composition is horizontal. So we just put them next to each other, and this is regular composition of linear maps. So then, for instance, if we do that here with these 2 things, we get this matrix C on the right, which is up to a scalar factor square root of 2. I promise they would crop up everywhere. A C0 gate. So this is why we had this thing for the C0 earlier. Yeah. And so any select diagram is built by just taking Z and X spiders and composing them vertically and horizontally. Yeah, and there are a lot of symmetries there, which is really nice. So you can calculate the matrix of the left-hand side here, where we do a Z and then an X. And you can calculate the right-hand side, an X and then a Z. And you can see that these matrices will be the same. And for this reason, it doesn't matter how we draw this line. So I will just draw it vertically. And this is why we had this representation of a C0 earlier. This is just the C0. So in general, only collectivity matters. So we can deform a diagram however we want. We can treat it as an undirected graph. And the linear map it represents will be the same. So I will just you can just take these things and move them around anywhere. And this makes it easier to implement them in software because you can just treat the data structures as an undirected graph. It's really nice. Yeah, so in summarize, we have two types of generators. You can compose them horizontally and vertically, and you can connect them however you want. And this always represents a linear map. And how powerful is this representation? Well, it turns out that any linear map between qubits, so any linear map from like a 2 to the n dimensional space to a 2 to the m dimensional space can always be represented by a ZX diagram. Generally, an exponentially large ZX diagram, of course, because otherwise some complexity theoretic things would break, but you can always do it. The question whether you want to depends on how nice you can represent it. Okay, so to recap again, so for the Clifford-Pastis circuits, we can represent the C0 gate, the S gate, the Hadamard. I have this special notation of a yellow box. This is actually just some synthetic sugar. You can actually expand this using the UvA decomposition of the Hadamard into spiders. But for now, like this yellow box will be fine for us. The T gates, and then as I said, like you have like a state preparation, and here I introduced like a Boolean variable x. So x is either 0 or 1, and this makes it easy to represent either cat0 or cat1. And then we also have this post-selection thing, this sort of bra. There's also like a bra x, which is x is 0 or 1. So whenever we see an x pi, this sort of means, oh, there's going to be the computational basis state here. For instance, if you want to represent the calculation of a single amplitude, we have this unitary U here. Well, we know how to represent unitaries as a ZX diagram, just do gate by gate. And then if you want to plug in this all 0 cat state, we just plug in all these x spiders at the start. And if you want to calculate its amplitudes on like a certain like post-selection, we can just plug in these x1s to xn's. So this allows us to represent amplitudes as ZX diagrams. If you want to represent marginal probabilities, we can use something that we call the doubling technique. So we just take sort of 2 copies of the circuit, take the adjoint, and then you connect together the wires that you are marginalizing on, so that those are the probabilities that you want to sum over. So this would be like the marginal probability of observing x1 to xk, and then like not caring about the results in the other qubits. So this is a way to represent marginal probabilities. Okay, so far the general introduction to ZX. Now let's see what we can actually do with this thing. So the first result I want to talk about, which is going to take the most time, is how to simulate, classically simulate quantum circuits using the stabiliser decomposition approach. Okay, so first, is there any questions generally about the ZX before I move on to this specific result? Cool. All right, so the problem here is how can we somewhat efficiently simulate quantum circuits. So we expect, like, we can't do this efficiently in general, right? But hopefully we can sort of push the boundary of what we can simulate. And I'd say that broadly there's 2 different ways to do this. There are the tensor network based methods. And there's like lots of techniques in here. It's a very well developed field in say quantum metaphysics. And generally, if you do these kinds of methods, it will scale exponentially in the number of qubits. There are some exceptions, like for instance, if you allow noise, you can do better. You can sort of analyze the global structure of computation, you might be able to do better. Like there are, for instance, things if your computation forms a tree, you can sort of very efficiently calculate it. But generally, exponential in the number of qubits. Then there's sort of a different approach, which was really developed in the context of quantum computing, because tensor networks have existed for much longer. And these are the stabiliser decomposition based methods. And that's what this talk is going to be about. And again, there's like 2 sort of different tracks there, the stabiliser extent and stabiliser rank. I'm just going to be talking about stabiliser rank. So let's see what this is. So there's a famous theorem called the Gottman-Knoll theorem, which I'm sure many of you have heard of, which says that if you have a computation, a quantum computation, which consists of starting with a stabiliser state, for instance, the all 0 computational basis state, and then we apply just Clifford unitaries. So these are your C0, your Hadamard, your S gate. And then you apply a stabiliser measurement. So for instance, a computational basis measurement. This can be efficiently classically simulated, like very efficiently actually. So this is sort of like a fragment of quantum computation where there is no computational speedup. This can just be done classically. There's an observation here, which is that the stabiliser states actually span the entire set of quantum states. So that means we can always write any quantum state as a linear combination of stabilizer states. And we need a number of terms of this, which are called chi, and we call chi the stabilizer rank. Okay, and so it turns out if you like have a computation which involves states which only have low stabilizer rank, you can sort of efficiently simulate them by exploiting the Boltzmann-Knoll theorem, that you can do that efficiently. Okay, so how does that work? In a bit more detail. So let's say we start with the Clifford plus T circuit. So the Clifford plus T gate set is an approximately universal gate set. So it means we can approximately represent any quantum computation using this. So let's just restrict to Clifford plus T. Each T gate can actually be represented as a magic state injection. So that means that instead of a gate with a T, you have a certain type of ancilla that you prepare, and then you inject sort of the phase of this ancilla into the circuit using a Clifford gadget. So this makes sort of that gate into a Clifford gate, but at the cost of having an additional ancilla, which is prepared in a specific state that we call a magic state. Now so if we do this with all the T gates, that means our entire computation is just Clifford unitaries. But then at the start, we have some non-Clifford input states, some non-stabilizer input states. So then we can decompose by using the stabilizer rank of this thing, we can decompose it into a sum of stabilizers. So that means we've written our entire computation as a sum of Clifford computations, a sum of stabilizer computations. So we can efficiently simulate each of the terms in this sum, and we just add the results together. Here we go. So this is a way to simulate quantum computations. But there's a catch, which is that the stabilizer rank of k of these T magic states scales exponentially with k. Okay, so if you have k of them, you need two. You have an exponential number of terms in your sum that you need to sum. But it's not just 2 to the k terms, and that's what makes it interesting. Like we can get better scaling than that. Okay, so this T magic state, which we're going to write as cat T, it's this specific state. It's like equal superposition of 0 and 1, but with a phase of pi to the 4 in there. And the stabilizer rank of this is 2, because, well, 0 is a stabilizer state, 1 is a stabilizer state. It's obviously some of these two things, right? So the stabilizer rank of this thing is 2. That means we could decompose each in sequence, and we would get 2 to the k terms. So this is the worst way you can do it. But already, if we have 2 of them, we can observe that we get these 4 terms, but we can group them together in a particular way, right? We can group them together in like these Bell state things. So we get like a Bell state with an I phase, and we get the 0, 1, 1, 0. So these are 2 Bell states. Bell states are stabilizer. So that means we actually have this thing as stabilizer rank 2 as well. So this means if we decompose these T gates pairwise, we don't get the scaling 2 to the k, we get a scaling of 2 to the 0.5 k. So we're doing like quadratically better already. So there are like more complicated decompositions. A recent result by Kasim, Pashan, and Gosset shows that if you have 6 of them, you can actually decompose them into 6 terms. And like this gives you a scaling of 2 to the alpha k, where alpha is the 0.43. So this is again a bit better than 0.5. I'm going to be using this label alpha as sort of like a general like exponential factor. So it's going to tell you like how efficient decompositions are. Yes.
So in the previous slide, you said this stabilizer rank scales exponentially. But you mean at most exponentially? An exponential lower bound.
So yeah, when I say exponentially, I mean we have a exponential upper bound.
Right.
If it were like say polynomial, then like BQP,
right,
is P and all this other stuff.
So I mean, yeah, lower bound is still open.
Yeah, the lower bound is still open. There are like there are lower bounds, but they're like linear. Like, so that's not that good. Yeah.
So I guess what you care ultimately about is what's kind of this approximate rank, right? So you allow, if I say I allow for an error epsilon, then I take k to infinity, and then after taking k to the infinity and taking the log and divided by k, I take epsilon to 0. That's the most.
Yeah, I don't think it has been studied in sort of this level as asymptotic formality, but there is a notion of approximate stabilizer rank, and this does give you lower bounds than if you were to do it with exact.
Like, for example, in entanglement theory, if you look at the Schmidt rank, this is really nasty. So like it's really difficult to manipulate. But then if you smooth it out, then you get nice things like the entropy of entanglement.
Yeah, you can definitely do stuff with approximate rank. For this talk, I'm only going to talk about exact stuff. So there's not going to be any epsilons in this talk. Okay, yeah. But actually, so for this alpha, like in this talk, I'll show like a way to even better than what was here. Okay.
Sorry.
Yeah.
So how is this result obtained for 6? Like.
So there was originally a result of 6 T gates into 7 terms, and this was found by like a simulated annealing type thing, where like you say, okay, let me try to 6 to 7, and then you have some terms, and then you calculate the fidelity with the state you want, and then you apply some Clifford unitaries to it, and you check the fidelity again. And for some reason, this converges. I don't really understand why.
Like it's a computer assisted proof, so that's like.
Yeah, but then you can easily verify that once you have it, you can just calculate it in your maps and you see that it's equal. But the 6 into 6, I'll get to that later because it's going to be relevant for the stuff that we did. Yeah, the way they found it is they have like, they don't look at the tensor product of T metric states, they look at something called a cat state, and they realize there's a connection between these two things. Yeah, but we'll get to that. Okay, so our idea was to do this type of simulation, the stabilizer rank simulation, but use SELEX diagrams instead of circuits. And the benefit of that is that you can then optimize the intermediate SELEX diagrams, because with, like, say, circuit optimization algorithms, you can only optimize a circuit, but the benefit of SELEX is we can represent non-circuit-like entities. We have these like amplitude things, and we can still optimize the diagrams. And this allows us to reduce the T count, the number of T gates, which means we get like less severe exponential scaling. Because if you can cancel additional T gates, you get better scaling, hopefully. Okay, so what's a new algorithm that we propose? So we take our Clifford plus T circuits, we write as a SELEX diagram, or actually we take our Clifford plus T amplitudes, we write as a SELEX diagram. We simplify the diagram with your favorite algorithm, with whatever algorithm you want. I'm not going to be talking about the details about the ones we use, but then you pick some spiders that have like T-like phase or a non-Clifford phase. You decompose those using like a stabiliser decomposition. Then you get a sum of diagrams. Then each of the diagrams in turn you simplify again. Hopefully this cancels additional nice stuff. And then you repeat the decomposition optimization until your diagrams are simple enough that you can actually calculate the value of them directly. Yeah, and you evaluate all diagrams, you get your outcome. Okay, so let's go through this in a bit more detail. Yeah, so there's one note I must make, which is this notion of strong simulation versus weak simulation. So weak simulation is sampling from a quantum computation. So this is what people are usually interested in. Like if you want to say spoof like an experiment, you want to weakly sample from the quantum computation. Strong simulation is that you're calculating probabilities of events. So you're calculating what's the probability I will observe this outcome of this thing. And generally, strong simulation is harder. Like weak simulation is PQP complete. Strong simulation is sharp P complete, which is thought to be like a much harder computational class. And in terms of like for strong simulation, you can get to weak simulation. I'm like our methods are strong simulation. So I'm only going to be talking about strong simulation, and there are ways you can get back to weak simulation. I can talk about this later if you want, but for now, we're just going to be calculating amplitudes, calculating marginal probabilities. So this is the harder one. Yes, we're doing, and even we're doing exactly. So not even approximating the value, but giving like the exact value. Yeah, so we've already seen how we can write a circuit as a SELEX diagram. So let's talk a bit how we optimize SELEX diagrams. So there is a set of rewrite rules for SELEX diagrams that we call ZX calculus. This is the reason we really care about SELEX diagrams, because you can rewrite them using these graph rewrite rules. I'm not really going to be talking about these, so not going to be super relevant for this talk. It's just that these are like a set of rules you can do a lot of things with. This set of rules actually is complete for the Clifford fragment. So that means any equality between like Clifford computations you can prove using just these rewrite rules. But you see that these rewrite rules are like bidirectional. You can apply them left to right or right to left. So for like an optimization strategy, it's not really useful because you want to decrease some metric, right? You want to use something more directed. So that's what we developed in this other paper, reducing T count with SELEX calculus. I'm not going to be talking about the details. The important parts are, if we're given a SELEX diagram, we make a distinction between the spiders that carry a Clifford phase, this is a pi/2 multiple, and the non-Clifford phases, these are say pi/4 multiples. And we can remove any spider with a pi/2 multiple from the diagram. So we can do some graph rewrites so that the spider is now gone, so that the resulting diagram will only contain non-Clifford spiders. That's sort of the goal of the strategy. That makes the diagram smaller, and that means it's more likely to find cancellations of the T gates. So if you do that, you will get diagrams like this. The reason it looks so messy because this is an actual real diagram of optimization we did. And here I've drawn this this blue line. This blue line means there's a Hadamard gate on this edge. And as you see, like I'm not sure if it's going to be clear from the back, but every spider here carries like say 3 pi over 4, 7 pi over 4, they're all odd multiples of pi over 4. That means they're non-Clifford. We can sort of see two types of spiders. We have the things on the bottom, which are sort of like a regular like single spiders with a non-Clifford face. And these things on the top, which are actually like a pair of spiders. So we have like a spider which has no face on it, connected to a single arity spider with a non-Clifford face. This unit of two spiders, we call these face gadgets, and they crop up many times to optimization and select diagrams. And they're going to be really useful like in the next few slides. One observation is that the spiders on the bottom are connected to whatever. The face gadgets are only connected to the spiders on the bottom. The face gadgets are not connected to each other. So that's one of the features of these diagrams, and it's also one of the things we can use for more efficient decompositions. Okay, so we get diagrams like this, and these are nice for a couple of reasons, or there's an important part. Is that every spider carries a non-Clifford face, or is part of a face gadget. So here I've drawn it in a different way. This is sort of like a type of unitary. This is like a Ising type interaction, if that means anything to you. It's like a ZZ exponential. But particularly what's interesting is if our original circuit has KT gates, then the diagram we get out has at most 2K spiders. This is independent of the number of qubits or number of gates. Okay, so if you had a circuit with 1,000,000 gates but only 20 T gates, then the diagram we get has at most 40 spiders. So it kills all the Clifford stuff. The reason this is possible is because of this Gottsman-Knil theorem that also gives you like a normal form for Clifford things. Okay, so that's how you optimize select diagrams. Then let's get to decomposing magic states. So this is this 6 to 7 magic state decomposition that I talked about a bit earlier. So we see on the left-hand side, we have 6 of these pi over 4 spiders. These are like your magic states, it's a tensor product of magic states. And on the right, we have 7 terms. So there's a sum of 7 diagrams. And each of these diagrams we see only has like a pi over 2 faces in there. So either 0, pi over 2, pi, 2 pi over 2. So that means they're stabilizer diagrams. And you see this looks quite random, and that's because this was found using like a simulated annealing type search. But this is how these kind of things look. Okay. So how we apply this thing is we essentially pick some spiders. So in this case, you pick 6 spiders because it's about 6 magic states. We unfuse like a pi over 4 face. This is one of the rules of select calculus. You can almost unfuse these faces, and then we have these 6 things here. And we just apply the decomposition there. That replaces these non-Clifford things by Clifford things. Our optimization strategy can kill all the Clifford things. So now we can simplify these diagrams so they become smaller. And we can repeat this. We essentially pick these at random. We haven't really found a good strategy for that, for which ones we should pick. We know it matters a lot. Like we've done some more exhaustive searches, and like it can bring down the number of terms you need from like tens of thousands to like 20 if you pick the right ones, but we don't know how to pick the right ones. This is like one area where we want to improve. Yeah, so after the first decomposition, we have 7 diagrams. Like again, there's better decomposition than this, but this is just one that we had first. And then we repeat the whole procedure for each of the diagrams. And we have 7 times 7 diagrams. And you just repeat this until the aren't 6 magic states decompose. And at that point, your diagrams are small enough, you can just calculate the value of them directly. And then you sum all the values of these amplitudes you get, and then you're done. So how well does this work? So there's 3 benefits to doing it this way. So the first is an asymptotic benefit. And this happens when no T-like phases are killed. So the best benefit is like if the optimization manages to remove additional T gates, because this thing is exponential in number of T gates. But let's suppose no T phases gets removed by the simplification. What that means is that every diagram you get needs a constant number of rewrites. So that's nice. And the size of the diagrams was order k, where k is the number of T gates you start with, right? So that means that the graph rewrites costs like order k squared, because you're like toggling the connectivity of your graph. We have these 2 to the alpha k diagrams, where alpha was this particular constant that we have for the stabilized decomposition. So it means the total cost of the algorithm is 2 to the alpha k times k squared. a previous algorithm had 2 to the alpha k times k to the third. And the reason for that is because they decompose everything all at once. And then they use like a Gotsman-Knell stabilizer simulation algorithm to simulate them. And this algorithm has a complexity of k to the third. So the reason we get this lower exponential there, this lower degree there, is because we're sort of doing early optimization. So we're making the diagram smaller as we go, and it prevents doing double work. So this is the reason we get this asymptotic benefit. So that's one sort of concrete benefit. This is like relatively small because, well, we have an exponential in there and a polynomial. So obviously the exponential is going to be more important. The other benefit is we can use better decompositions. Okay, so for this I have to talk a bit more about this result from Kasim from 2021. So they had this 6 T-gates into 6 stabilizer term decomposition. And the way they found it is by using cat states. So a cat state is defined by this thing, but really I found it nice to think about them in ZX, because in ZX they have a really nice representation. And so what they do is they find like good decompositions of cat states, and then they realize that if you have a bunch of T magic states, you can write this as a sum of 2 cat states. So that if you have a decomposition of cat states, this lives to a decomposition of T states. So that's what they do. But because we have ZX, and because cat states have such a nice representation in ZX, we can just use cat states directly. That's a nice benefit of having. So the decomposition they find, and if you write them in ZX, is this thing. So on the left, we have 6 of these pi/4 phases. And on the right, we only have 3 terms. This is really good decomposition. This gives us an alpha of 0.264. In fact, you can do even better, because if you have a cat4 state, you only need 2 terms. This gives alpha is 0.25. And again, this number is in your exponential, right? This makes a big difference if this number is a bit smaller. Yeah, and then you can sort of use these to like also get decompositions for cat5 and cat3 and cat2. And the reason we care about these cat states is because they're actually phase gadgets in disguise. So on the left, we have a phase gadget. We're just sort of bending some wires and unfreezing some phases. We see on the right, on the top, that's a cat state. So an n-legged phase gadget is just a cat n+1 state. So if we have a diagram, if it contains phase gadgets, we can use the cat decomposition directly. We don't have to go via the magic state decompositions. Yeah, so as long as the phase gadgets, we can use these decompositions. But in fact, we can also do some other nice things. Because suppose there aren't any phase gadgets. Well, it turns out we can use this thing which we call a partial decomposition. So first on the left, we have 5 magic states. We realize we can write this as a post-selected cat state. So we have here, like on the top, we have sort of a post-selection to -4, and you can show using ZX that these things are equal. It's just like some fusing of some phases. And then we can decompose this cat6 state into 3 terms, because we know we have this decomposition. But now each of these 3 terms contains a single pi/4 phase. So they're not stabilizer states, they're almost stabilizer states, right? So on the left, we have 5 sort of magic states. On the right, we have 1 magic state. So we're trading 5 magic states for 3 terms and 1 magic state. So effectively, this is removing 4 magic states for the cost of 3 terms. This gives us a 4×3 decomposition. And this gives us a alpha of 0.396. And so this is one we can always use, because on the left-hand side, we just have a tensor product. And this 0.396 matches something that Kasim et al. They found it like asymptotically, but we can use it directly. So this is like a better asymptotic bound than what they can use. Yeah, so this means that not all stabilized decompositions are created equally. There's like an actual preference for things you want to decompose. So first we want to look for particular phase gadgets, because they said they have the best exponential scaling, right? So phase gadget with 3 legs is the best one. Then 5 legs, 4 legs, 2 legs. And if there aren't any phase gadgets, it turns out for higher arity phase gadgets, there's also better decompositions. But for now, let's simplify and stick to this. Then you can decompose any 5 T spiders and you get alpha of 0.396. Okay, so that's a second benefit. That's quite a large benefit. So as I said, there's 3 benefits. We have this preventing double work. We can use better decompositions. So the optimizations remove additional T-gates. And in practice, this turns out to be the most major benefit. I could show some benchmarks, but I want to talk about some other stuff as well. So it's just like for certain structured computations, these optimizations can remove many additional T-gates. And this makes it that you can simulate much larger circuits. Like we could simulate 50 qubit circuits with like 1400 T gates, because we had so many cancellations of these T gates in just a couple of minutes on a laptop. But this really depends on like the type of circuits. Like we also tried with random circuits, and there's less structure there, and then less cancellations happen. So there, that turns out to work less well. So this is what I want to say about the first result. So is there any questions about that?
I guess you've no real theoretical amount on how many T gates.
Also, in the next result I'm going to talk about, you can view it as sort of a specialized case over here, and then by smartly picking which things to decompose, you can get like a better bounce. And,
So you're fighting for a constant and an exponent.
Yeah.
Do you think that's the right scale at which to work in this setting?
what do you mean?
I mean, do you think you really need exponential lower bound on this rank? Or
Well,
could it be-
if it was sub-exponential, that means the separation between BQP and P would be sub-exponential, which would be very weird.
already, if it's like to the root K.
Oh, that's a good question, because then it would be like depth dependent, I guess. So that would not be, yeah, that's right. Yeah, no, I guess it could be 2 to the root K. But then you would have to use a fundamentally different technique to get there, because then you can't get there with just like iterating with precision. You would have to have, for every size, there would be something special about that you can exploit to decompose it. So you would have to get there by a completely different technique, which might be possible, but I don't know. I know there is a result that says that if you can get this alpha down to order 10 to the -8, you would improve on the best set solvers, because you can encode a set instance into quantum computation and then use this thing. So even if it's linear but very low linear, it would improve on set solvers. So that makes me think it's unlikely that there would be like a sublinear thing there. Yeah. Okay. Okay, so the second result, which is sort of an application of this thing to simulating IQP circuits. So first of all, what are IQP circuits? So it stands for instantaneous quantum polynomial. This was thought of by Shepard and Bremner in 2009. And this is a specialized quantum computation where you input just the all zero state. Then you apply a circuit, which is the Hadamard on every qubit, then a diagonal unitary, and then another layer of Hadamards. And then you measure on a computational basis. And this diagonal unitary consists of polynomially many diagonal gates. Yeah, this is where like the polynomial in IQP stands for, and the instantaneous stands for the fact that the unitary is diagonal, so there's no time information. So you can view it all as happening instantaneously. And they were interested in this as a toy model for like where you could already do computationally hard things, like things like Ising type physical systems and models. It was shown in 2011 that if you could efficiently simulate IQP circuits, this would imply a collapse of polynomial hierarchy to the third level, based on, was there some assumption? No, it was just this collapse. And also later there was like a difference based on like some stronger assumptions. You could also get a collapse, but then it was on like here they assume like a multiplicative error in simulation, and you can also get an additive error in simulation, and you can also still get a hardness, but you need some harder assumptions. For our case, what's relevant is that Bremner, Montanaro, and Shepard in 2017, they showed that even simulating sparse, random Clifford plus T IQP circuits is hard, if you have some assumptions. Sparse here meaning that every qubit interacts with a logarithmic number of other qubits, like order logarithmic. And Clifford plus T, we'll get to that later, because these structures are constructed in a very particular way. And the nice thing about this last class of circuits is that they can be implemented in reasonable depth on the 2D architecture. You have to sort of go outside the IQP framework, but you can implement it on like a physical system. And you can make them tolerant to some noise. So you can get the calculation you want out of them, even if there's some noise in the system. So they suggested this might be a nice candidate for quantum supremacy sampling experiments, because this is sort of very simple circuits. Yeah, so we were looking at these types of circuits, seeing how well can we simulate them. Like, are they indeed a candidate for quantum supremacy? Okay, so how are these random circuits actually constructed? So so remember we have our qubits are all prepared in the 0 state. We apply Hadamard everywhere. Then on every qubit we randomly apply a power of a T gate. And on every pair of qubits we randomly apply a power of a controlled S gate. So this is just this 111i diagonal gate. Note that control S to the power of 4 is just identity. So this means the probability of interaction between qubits is 3/4. This is in the dense case. So they also studied the sparse case. For now, I'm mostly going to focus on the dense case, but the sparse case is easier to simulate. And if you write this type of thing as a Z diagram, you get this thing. So we have these things on the qubits. They are like the T gates, and this XN sort of encodes like how many times have you applied a T gate. And these CS gates, turns out we can sort of represent these as these phase gadget things. And like phase gadgets, well, we know we can do nice things with those. And so again, if this Y on a phase gadget is like 0 or 4 or 8, that means you can sort of make this connection disappear. So we get this kind of graph structure where there's only an interaction there if there's an interaction on the computation. In fact, we can make this connection to a graph more clear if we think about calculating amplitude of an IQP circuit. So again, we're doing strong simulation, we're calculating amplitude. So here where I've inputted the all 0 state, and we're post-selecting to the all 0 bra. This is like without loss of generality, because if you want to post-select to some other amplitude, this would just result in some different phases on the diagram. So we can just stick to just having all zeros. And we can simplify this diagram a bit using select calculus. And what we get on the right-hand side is now a nice graph-like thing. So every qubit, which is like these x1 to xn, they're sort of your vertices of your graph. And then this red thing, the red spider connected to the Y, that's like your edges. So there's like an edge between two qubits precisely when there's an interaction in your computation. So we now have like a graph representation of an IQP amplitude. Now we use a very particular type of stabilizer decomposition on this, namely a very simple one. So this thing on the left is we have a single non-Clifford phase, or even a Clifford phase, we don't really care at this point. And we decompose it into two terms, which is just the computational basis state terms. And we will apply this to our qubit, so to our x1 to xn. We apply it to one of those. So this decomposes the diagram into two terms. And then the diagram we get will contain shapes like this, because this introduces like an A pi kind of thing. And it turns out that if you fuse into the diagram, those things can combine. So that means those phases just combine. So if you remove a vertex like this, so an X spider here, then it also cancels all the edges it's adjacent to. Okay, so that just literally removes the vertex from the graph and also all the edges it's connected to, at the cost of two terms. So this suggests an algorithm. So the algorithm we use is we identify the largest independent set in the graph. So an independent set is a set of vertices that are not connected to each other in the vertex, in the graph. And we decompose all the vertices not in the independent set. And that means, since we're just removing these vertices from the graph, that means we're left with a completely disconnected graph. There's just spiders there that are not connected. That means we can calculate the value of the diagram we get very efficiently, namely in linear time, because well, every spider is just a number, and we just multiply those numbers together. And then we can just sum all the terms we have, and we have calculated the value efficiently. The reason this works very nicely, so first of all, calculating the independent set is exponential time, but exponential is so gradual it's not going to be relevant for the machine we're looking at. And second, we're working with random graphs, and those turn out to have relatively large independent sets. So first of all, if we find an independent set of size k, then the complexity of this algorithm is complexity k times 2 to the n minus k. So again, we're decomposing all the vertices not in the independent set. So we get 2 to the n minus k terms. And then once we have a term at the end, we can evaluate in linear time. And the graph is just the independent set. This has size k. So the complexity is k times 2 to the n minus k. A classic result from 1972 says that if you have an Erdos-Renyi graph where there's a probability p of having an edge between two vertices, that means that you will have an independent set of size, this expression. In particular, in our case, p is 3/4. So p equals 4. And that means we have independent sets of size log 2 of n minus log 2 of n. Again, this is with like high probability, like this. It's like with very high probability we have an independent set of this size. And that means the complexity of evaluating the diagram like this will be this expression. So log 2 of n over n times 2 to the n. This is still exponential number of qubits, but now we have this nice over n factor there, which helps a lot. Because if you compare this to using a standard state vector simulation approach, where you just like you keep your state vector in memory and then you update it with all the gates in the circuit, this would be n squared times 2 to the n. Or if you directly use a stabilized decomposition approach, well, let's order n squared t gates in this thing. So this would get like terrible complexity. So this means by sort of smartly picking where you apply the stabilized decomposition, you get this nice polynomial factor improvement there. And in practice, this also works really well. I'll show a graph later. There's an alternative algorithm which gets a slightly better complexity, and it's also a bit more interesting, I think. So instead of considering the graph of all the connections between qubits, we only consider a connection in the graph if the interaction is non-Clifford. So we have these CS gates and powers of CS gates. Well, CS squared is just a CZ gate, which is Clifford. So if we say ignore those connections where CS squared happens, so we only have, then what that means is we have a graph which is still a random graph, still an Erdős-Rényi random graph, but now the probability of interaction is 1/2. And that means we will find larger independent sets, which is nice. So again, we can find an independent set of this sort of non-Clifford interaction graph, and we decompose all the other vertices. What that means is that we now have a graph that is not completely disconnected, but all the connections between the spiders will be Clifford, so they won't introduce additional T phases. So the only T phases appear on the qubits themselves. And again, since these are random, we expect about k over half T gates there. So that means we can now apply a stabilized decomposition algorithm to the graph we get. And that will give like a nice result here. So you can calculate what the complexity of this thing is, and you get this expression where alpha is this exponent, is this constant we found, this 0.396 we found earlier. So remember the previous time we got 1 over n, and now we have 1 over 2 to the minus alpha, so this is like about 1.6. So we get a slightly better exponent here. In practice, we haven't implemented this algorithm because using these stabilized decompositions, you have so much higher constants, it's probably not going to be faster than the simpler algorithm in relevant regimes. But I do think it's interesting, you can sort of combine these techniques, you can stack these techniques to get a better asymptotic bound here.
Here or smaller alpha is better.
Yeah, so if you find a better stabilized decomposition approach, then also this method will improve. But well, you see it's 2 minus alpha, so even if alpha is 0, you won't get better than n squared. So if you could use some other assumptions that would make it that your independent sets are larger, that would get a much larger effect. Like if you can somehow have a computation that has like a large independent set, that's the thing you want. So Julian, the co-author, he implemented this. And so we saw that this was run on like a single CPU core on the laptop. And we found that like in the sparse case, so 1 sparse means that every qubit interacts with like 1 times log n other qubits. We see that we can simulate like a 50 qubit circuit in like see that's about 10, 20-ish seconds. But like in the dense case where we have like this interaction probability of 75%, we see like we can get up to like 30 qubits in like a couple of minutes. And this is like a very parallelizable technique because everything is sort of decomposed on its own, so you can just like give them to many nodes in the cluster. So we estimate if you have like say like 100,000 CPU cluster, like maybe fast CPUs, you can simulate like easily a 50 qubit circuit. If you go to a large supercomputers, you can maybe even go up to 70 qubit circuits, like in the dense case even. So this is sort of saying that like for quantum supremacy experiments, it's going to be hard to show that like this is actually going to get you into a regime where like a classical computation cannot do it. So yeah. So I think that's interesting that you can just like use these stabilized decompositions to actually like get into this sort of quantum supremacy regime of things. It is interesting that these like sparse things. So in the paper we have like better bounds for these sparse circuits with like better polynomial prefactors. But here we see that this very neatly follows like a more gradual exponential curve. So this sort of suggests that we should be able to derive even better bounds, which have like, instead of having a 2 to the n, it should be like some kind of 2 to the beta n, where beta depends on the sparsity of your graph. But we don't know how to do that. Okay, that's the end of the second result. I also have prepared a third result, but I don't think I have time for that. So let me just quickly say what the result is without giving any explanation of how we got there. This is like it seems very different, it's actually quite related. So we find a quantum-inspired solution to counting the satisfying assignment to Boolean formula. So what it means is if you have a conjunctive normal formula, so this is like a Boolean function, then the problem of a sharp set, this is how you pronounce it, sharp set, is counting the number of satisfying assignments to this function. So it's counting how many times does this evaluate true. So in set, that is satisfying, you ask, is there a solution? In sharp set, you ask, how many solutions are there? So obviously this is a harder problem. There's a number of complexity parameters that you might be interested in. And obviously the number of variables, that's sort of the standard like size of the problem. K is the maximum clause size, which is like for tree sets, like K is 3, like you have 3 variables appearing in every clause. M, the number of clauses, and then delta, the clause density. So how many clauses are there? Oh, this should be M over N, not N over M. The clause density. And we give the first non-trivial algorithm for a sharp set that works for small enough clause density, but still like relevant for practical use cases, which is independent of K. So there were previously known results, but they sort of scale up close and closer to the end for the trivial bound when K increases, but ours independent of K. Namely, yeah, this thing. So we find an algorithm that solves it in time, well, this thing, with n plus m, so m is the number of clauses. So this means this is better than a trivial 2 to the n bound when the clause density is smaller than 2.25. And this is still relevant. Like there's this competition every year for trying to solve these sharp set instances, and many of the instances have lower than 2.25. So this is relevant for like in this review. This has an interesting corollary, which is the hardest sharp set instances must have a delta larger than 2.25 if the strong exponential time hypothesis is true. And this is as far as we know, this is the first like result of this type. Like this wasn't previously known where the hard instances would lie. So this is nice. I'm not going to say anything about how we got there, but it has to do with Zexcroft mistakes. Yeah. So the conclusion, ZX can be used to greatly speed up stabilized rank simulations, and also in these more specialized use cases, you can get better algorithms than was previously known. For future work, one of the reasons I wanted to give this talk is because I'm writing a grant on doing this kind of stuff with additional things. So if you're working on classical simulation, or tensor networks, or condensed matter even, or like Boolean formula counting, come talk to me, and like we can maybe like say something about that in my grant that we're gonna collaborate or something. So, yeah, that was the talk. Thanks.